Okay, we're going to get started with our panel, kind of our closing panel. So let's see, Dr. KC Liu.
Supervisor KC. I'm very honored to be here, be the moderator for this session. I think people here, some are from the Taiwan community, and Professor Ye, and Jack, and Ricky, and okay, Ali, Matthew, and Elder. Okay. Later, I will in the session I will let you briefly introduce yourself first. Okay. So Ali, your turn. Okay. Okay. Okay, Jack. Yeah. Yes. Okay.
Okay. Good. So Ollie Ors with NXP Semiconductors, Global Director of AI Strategy and Technologies.
I'm Matteo Maravita, responsible for APAC AI Competence Center, ST Microelectronics.
Hello everyone, I'm Samuel from HiMax. I'm responsible for the AI processor chip design.
Hello, I'm Ricky from Tomofang and is responsible for the AI system design. Thank you.
So this is Zhong Tai-Ye, and I'm from the National Jiao Tong University, Yangming Jiao Tong University, yes.
Okay.
Hi everyone, I'm Jack. I'm from AGI Taiwan Group. I focus on the MCU AI.
Okay.
Hello everyone, my name is Eldar. I'm part of the AI COE team in Renesas. I mainly work on the AI tools and compilers.
Okay. Okay, good. Because already some question I plan to raise here have been answered in the morning and in the afternoon in the all the speak here. So I suddenly might want to change my mind to randomly ask some question. Okay, just a free chat. Okay, the number one question I'd like to ask some about research question for Professor Ye first. Okay, so I know you have a paper appeared in HPCA last year and this year, right? So I'd like to know from the cloud to edge, even for the tiny, what's your opinion for the research, the gap, how to utilize, how to leverage the cloud to the tiny, or even today we will tiny become the Edge AI Foundation. So I think you have some idea about when you're doing research, where there's a gap. I'd like to address this issue. Maybe later other panelists can follow the same question to give answers. Okay, Professor Ye.
Yes, so this is a good question, and basically we found more and more applications used in these edge devices. We call it tiny emitter. We try to achieve the green computing, or just use more less energy consumption, or use the less cost to just employ the AI applications on the edge. So I think the biggest challenge is when we apply or deploy the AI models on the edge devices, the two challenges. The first is the memory. Okay, we do not have a large memory space or the memory within our edge devices. So the second one is the computing power. Okay,
yes.
We do not have the large GPU in our edge. Okay, so these challenges drive us to just to see how to just squeeze our AI models on this edge device become possible. Okay, so I think some of the possible solutions, okay, to just enable us to enhance the programmability and also enjoy the performance, okay, and the power efficiencies on this AI or the tiny ML. Okay, so what I want to say is the first one is the model compiler. Okay, so model compiler is a very key role to apply or deploy these tiny ML models on the edge devices. Okay, because the model compiler, they can just accelerate or facilitate this the flexibility or programmability, okay, and also optimize the language models or the CNN models on our edge devices. Okay, so the model compiler is the key one. And the second one is the promising of the recomputable computings. Okay, for example, we have the FPGA, or we have the new promising the hardware. For example, we have the coarse grain reconfigurable array, this CGI, or this architecture. And then we also try to see if the hardware platform can also apply within these edge devices, and to just enable more the TinyML or these AI applications become possible or become promising within the edge devices. Yeah. Okay, so we have the challenges and we have some solutions by using the model compiler or use this promising hardware to just advance the progress of the future AI or future TinyML applications.
Okay.
Yes.
Yeah. Thank you, Professor Ye. So, any people here want to give some additional notes?
I'll add. I mean, everything that we agree with everything that has been discussed. What we see is that that's very applicable for some AI models that belong in or start off in the cloud and trickle down to the edge, or get optimized, get quantized, pruned, and get optimized to be able to run on the edge. But there's also a class of AI models that belong in the edge or are created in the edge, and that's part of what we're also seeing. What used to be more the TinyML view on microcontrollers, so they never were belonging on the cloud or high-performance compute. They always belonged in a edge deployment. So you have these two classes, but I think it's very applicable in terms of that trickle down from the cloud of the model compiler, the efficiency compilation, because you have memory limitations, you have compute amount limitations. I fully agree.
Yeah, yes. So I think model compiler, this is the key word. Scamizer focus on model compilers. Okay, yeah, okay. So, and maybe next question I will ask about product, because the people here in this morning and afternoon, you have shown some your product already. So the question is about the roadmap. Because you have some MCU-based, but MCU with some NPU, but actually for AIoT sensors. So I'd like to know, from your point of view, by sensing AI, what will it be, what will you do, okay, about your product, the next generation, for this kind of by integrated sensor, for the data from sensor, high speed, low power. Okay, Matthew.
Okay, thank you for the question. Yeah, as ST, we already released in the market a few years ago a first sensor with the first, what we call the machine learning core. That time was a small core that was able to run only decision tree model, okay? And recently, 1 year ago, more or less, we introduced the first MEMS with so-called ISPU that has basically a small DSP inside the sensor itself that can run, is limited in terms of memory. It has an internal RAM memory of 20 kilobytes, but is far enough to run a lot of not only machine learning models, but also small neural networks inside the sensor itself. And I was very quick on that slide today, but you can see that we can run the same kind of model that before we were running on the microcontroller 3 years ago, like gym activity recognition, human activity recognition, to understand if I'm walking, running, like what we have on the smartwatches. Now, moving to the sensor, you are moving from 5 to 10 milliampere power consumption to 5, 10 microampere. So it's 1,000 less. And we see this that is a new trend. At the beginning, when we launched the product, the customers were still looking into it because we were the only vendor releasing this kind of product. So they were a little puzzled if they needed to go only with a proprietary solution like STMEMS, but now they recognize the value, and it's getting more and more popular. So we see also AI, small AI cores integrated in the sensor itself. But obviously, the key point of this solution is about the power consumption. So this is why this is feasible for only small models. If you are going to enlarge the model like to 100 kilobytes of memory and so on, and then or more performing DSP, then you are going to use more power consumption, and then perhaps it becomes less obvious that you want to run on the sensor instead of the microcontroller. But when you can differentiate, and you have a very big difference in power consumption, we see a trend there.
Yes, Matthew. So I'd like to follow the question in more deep. So because sensor is a time variant and a very real-time signal, right? So for the tool, just like a TensorFlow or some framework for the AI model, I think that is a traditional tool. So specifically for sensors, for your company, do you have any specific tools for sensor sampling for the AI?
We have basically two choices. So we can use the standard tool, like TensorFlow, Lite, any kind of deep learning frameworks at the end, or also sklearn, or we can use sklearn just to train the model. So and then if the model is small enough, and if it can fit 20 kilobytes, you can use any kind of deep learning framework. We have also another tool that is the NanoEdge AI Studio, that is an AutoML tool, but is just the difference is in the entry point in the, if you want an AutoML tool or if you want to craft the model by yourself, but the result will be similar. Both the tools will create a model that if it's small enough can fit into the sensor. So you don't need a specific tool for the sensor. Then obviously what we have is an additional piece of tool or software that is converting this model inside a specific library for the sensor itself, basically the compiler. Like you have for microcontroller, you have a specific optimized compiler for a specific architecture. In the same way, we have a specific compiler for the sensor. But all the tool chain before is the same. So the engineer can move the same algorithm to the microcontroller or to the sensor seamless, because the compiler is just the last step.
Okay. So Ali and Elder or Samuel, do you agree? Because you also a product company. Okay. Yes, Ali.
So, of course, we have different products doing similar things from our side. What I presented today, the EIQ Time Series Studio, is about that, creating models for sensor-based systems.
Yes.
So taking all sorts of sensor inputs from different sensors. We focus more on the processor side, but the sensor input can be any modality as far as we're concerned. As Matteo mentioned, it's the step afterwards. You can do AutoML, or you can handcraft tools with the EIQ software stack that we have. So you have all the Time Series Studio can create time series based models automatically for you, or you can handcraft within the EIQ toolkit your own model. So we support that same flow as well.
Okay, yeah. So, Samuel.
I'm Samuel from HIMAX. From HIMAX of view, because we adopt some use case in the computer vision using the MCU. So for the computer vision, the memory usage is very critical, just Dr. Ye mentioned. So in current tool, we found the memory utilization is common, not perfect.
Okay.
So it will impact the model size or inference speed. So if in the future there is a customized good model compiler or something can improve the memory throughput or usage, it will be benefit for the computer vision tiny ML application.
Yeah. Okay. So Elder. Okay.
it works now.
Okay. Yeah.
Thank you.
Good.
So mainly in the presentation today, as also Ali mentioned, that we also concentrate a lot on the microcontrollers and the microprocessors, but we do have application-specific sensors that are done specifically for specific applications, such as some of our kits come with Renesas sensors for gas detection, so it's very difficult traditionally to detect what kind of gases we have. So we provide some sensors, I forgot the name of it, I think it was a CMOT sensor, and it's able to detect what kind of gas you have in the environment. And it's, as we know that we generate a lot of data around us, and it's not reasonable to send everything to the processors themselves. So if we can do machine learning directly on the sensor, it alleviates a lot of the bus constraints. So we do have specific sensors that do ML, but I'm not sure if we can code what kind of ML model you have. It's already pre-provided for you.
Okay. Yeah. Thanks. Okay. So next question I will about the Taiwan community. Okay. And before that, I'd like to thank Odin, because original Odin is a panelist. He'd like to invite the community in Taiwan to encourage our Edge AI. So Jack, as I know, you are the founder of the Edge AI group. Okay. To empower by leveraging open source. Could you share your experience, maybe about the EVB or the multi-vendors chips, and the pro and the cons, because the supplies are all here. Okay, just take your opinion, please, Jack.
Okay, community to maintain it is very difficult. Now my community is called, it's named Edge AI Taiwan. About 10,000 more members. Every day I will share industry news and open source code and tutorial video for everyone. In community, first we can easily buy development board and can get the free tool chain. But now very confused is, for example, STM maybe have Cube AI, Nano Edge. STM maybe have NXP maybe have EIQ. Renesas maybe have Reality AI. So very different, not compatible. If we use like ARM CM6NN or CM6 DSP library, but different company maybe have different solution.
Yeah.
So developer need a standard, like MLPerf maybe have a different group for tiny. For example, if you use LLM or Gen AI models, you can download from the Hugging Face, but on the MCU, we cannot do it. It's very difficult to comparable every MCU provider. Yeah.
So that means for tiny ML world, there's not such a a camp can unify everything by tooling, by just like NVIDIA there. So I for the same question, I'd like to come to the product company like yours. Is it possible you guys have a alliance that make the tool more similar or can easy to, or because IoT is multi-segment, so the tools, the ecosystem can be variant, then will be heard to the programmer. Later I will ask the programmer, Ricky here, so I'd like to maybe check your opinion, because it's different tool ecosystem. So do you also, in your house, you suffer for that?
Yeah, no, in my house I don't use NXP microcontroller, I don't suffer, no. Part of the joke, I understand the request. I think, sincerely speaking, it's going to be extremely difficult in the next few years that the vendors will have exactly the same tool for, in terms of compiler and, let me say, to load, to compile the model for the specific microcontroller for many different reasons. First of all, we spent several years in developing our tools, and we have each of us have specific functions that we treasure, and we think that is a differentiating factor and is giving a value to our customers. So this is the first point. The second point is that in the future we saw that we are going more and more to MPU accelerated devices that are going to be different. So the hardware will be different, will need a different compiler. We are not going to converge only on one MPU architecture from ARM, for example. So obviously we will need a different compiler. What I can see there can be a convergence is more that I think is still very useful for the developers is on the Model Zoo portfolio. So when you need to deal with a computer vision, like today, if you need to develop an NLM solution, you go to Hugging Face, okay? And then you can find a lot of standard models that everybody in the community can use the same Llama 2.3 billion parameter or another models. So you have a Model Zoo that is the same, and then you can run the same model on your PC, on a Raspberry Pi, on an application processor. But inside the same community, you are using the same model. This is perhaps where there can be a convergence if there will be a place eventually where you may have a data set of Model Zoo of models that are specific for Edge AI. So you say, okay, instead of having 10 variation of YOLO in all the different versions, MP, and so on, we have a place where we have all the Model Zoo for computer vision, LLM, and so on. And then you can make your project with the same models, and then you just use a different compiler for the specific hardware. This is where I can see eventually there can be a convergence.
Mm-hmm. Yeah.
And maybe I'll add to that. There are a few points in that development flow where you can get into commonality. I think, as Matteo mentioned, it's difficult when you get lower into the hardware architecture or some of the benefits, because standardization limits differentiation, and we're all trying to differentiate with what is critical and what is better on NXP versus somebody else, or better on somebody else versus NXP. But where you have commonality is you have the model frameworks. There's a this started off with a lot more. There was Keras, Caffe, TensorFlow. Now we're seeing a lot more focus on PyTorch type of models. That's where the focus is from both academic and general development, like industry and research development. So there are a few model frameworks. So as long as the models, like in a Model Zoo, are coming from a specific framework or a few, there's that commonality. Then you also have commonality in types of operators supported by the hardware. So there you can also create opportunity to make sure that a model that runs on an XP will also run on a HiMax, on ST, on Renesas, and the end user, end customer can benefit from that, knowing that the model will run if they pick the different architecture, but it will run differently, and there will be different things on each of them. I think that's critical to us as semiconductor vendors differentiating.
Yeah.
So when we mention about the standardization of the tiny ML applications, I also want to talk about the benchmark.
Yes.
Okay, benchmarkings. Basically, we have the MLPerf tiny ML. This is the benchmark or benchmark suite. However, I'm thinking what is the spatial applications that is differentiates with the different from the general purpose or the AI applications shown on the cloud computing or data centers. So basically, in my opinions, I found the the benchmarks in the ML per tiny ML is just include some CNN models so far, but the size of this CNN model is smaller than the one shown in the ML perf
Yes.
benchmark. So the question is, what is the some distinguished or some unique applications for our, tiny ML communities or applications? So any opinions?
Oh, thanks, Professor Ye, for raising this question. Okay, help me ask here. So the question is benchmarking. Also, okay, Samuel can answer first. Okay.
Yeah, so I answer the uniform, the tool chain first. Because the tiny ML is basically running in the MCU, so this software and the tool chain is for bare metal, not like the SoC. There is a Linux layer, so the upper layer tool chain maybe can be reused to others platform. But for the bare metal tool chain, we need to consider the hardware architecture and the configuration. For example, different chip has different SRAM size or different accelerator. So maybe not easy to using the common tool chain to get the best performance. So for the second question from the Dr. Ye, I think the application for the tiny ML, from our product team of view, we found the tiny ML is a very good wake-up trigger in the system because they can maintain the always-on scenario under a very low power consumption. So such kind of the always-on wake-up trigger is very suitable for the tiny ML application.
Yeah. Okay. So okay, Elder. Okay.
Hello. Yeah. For the first question about the commonality, even though all of us probably use ARM, Renesas also has its own proprietary. But from a hardware perspective, we also add additional things to the ARM architecture that we leverage within our compilers. For example, from the heritage from Renesas, we have like many DMAs that we add to optimize the performance of the hardware itself. So having the similar tool chain across each vendor would kind of like remove that advantage each vendor has. And also even at a higher level, the compilers we use, we have GCC, LLVM, and then even ARM has its own compiler and IR has its own compiler, and they all have their advantages and disadvantages. It's because at a real-time operating system, you want to squeeze as much as possible from your architecture. So where you're going from an MPU perspective, you don't care as much to be as real-time as with MCUs. But going on a higher level, if you're trying to go from an AI compiler perspective, there is possibility to unify that realm, even if you have different MPUs. When you take from a higher framework such as PyTorch, TensorFlow, you can do an intermediate representation, which is going to be a commonality between the framework and your hardware. And then you can start lowering it down to your hardware itself. So you can have hardware aware optimization and hardware without the hardware optimizations for graph layers as well. So it is a bit possible, but from a hardware perspective, because we all have different hardwares, even though we use ARM, it's not very easy to have the same tool chain.
Yeah.
Sorry, let me add a comment. It's true exactly what he's saying, and I missed to add one details. So actually, it's possible to run a common software is a TF Lite interpreter on on the STM32, okay? And we can also run the ARM CNN libraries, okay? So it's possible actually to use a tool that is can be common with other vendors that are based on the ARM core, but exactly as Renesas is doing, also in our case, we have a specific hardware functionalities in the DMA and the memory controller. I think all of us have. So you can, if you use a common tool like TF Lite, you can do, but you are losing in performance. While if you use a proprietary compiler tool like of Renesas, ST and NXP, you get the best out of the hardware and you get the best performance. So it's a trade-off. So you want to have the same tool that is okay for everybody, but it's not so much performing, or you want to have the best. So how much is important the compiler for you?
Yeah. Okay, thanks, Matthew. Okay. So next question I raise to Ricky. Okay, being a programmer and a user, you are at the first front line, develop the code and meeting the customer. As I know, your company serve Amazon. You are supplier for the pet camera, right? So could you share your experience in using, in productizing the design by the chip, the system, the software, okay, from the user experience, and give some suggestion to all the others people here. Okay, yes.
Okay, so based on our over a decade experience in the product level AI system development, we would like, our core strategy is to separate the architecture into 3 layers. The first one is the sensor network layer, like the MCU level processors. And the second one is the edge AI, edge computing layers, like the smartphone or like the pet cameras. And the third layer is the cloud computing layers. And the first one, the sensor network layer, like wearable, like smart glasses, that work on the MCU can fetch the real world physical raw data and play as a noise reducer and also the event handler. And we believe that, so that's why TinyML can play in this role. And in this way, we can reduce the unnecessary data transmission to reduce the power consumption. And the second layer, the edge AI layer, like the smartphone, like the camera, can play a more powerful event filter that maybe we can use more MPU in this layer to provide a more powerful filter to reduce more unnecessary data transmit to the cloud. And in the cloud layer, we can use the more powerful models to ensure the performance of our AI service. So we believe that if we combine these 3 together, we can provide a more sustainable, more cost-saving, and more reliable AI service to our users. And so I would like to know more about how, is there any roadmap or any strategy to combine these 3 together? Because as I know that the MCU level and also the edge level, I think most of company has covered both of these 2 areas.
So it sounds like it requires multi-level solutions, but not the edge or tiny device only. So I believe we have the product, but product should consider from the whole system perspective, right? So maybe I think that some company like yours can give some idea.
So maybe I'll talk about the layers the way we see it, and touching on how it was explained. For us, the sensor level and the edge, in our view, is all edge.
Yes.
In the way we treat it at NXP at least. So microcontrollers and applications processors in our portfolio, we see that all as edge. And the tie into cloud for us is more at a higher level of management, where you need that cloud augmentation or cloud engagement. So a lot of what we're trying to do is to move more off the cloud onto the edge, create higher efficiency in terms of both costs and compute, but we still leverage the cloud, or some of our customers still leverage the cloud in terms of fleet management, in terms of ML ops management. So there's that added layer that is a higher level application layer that is happening on the cloud to manage more devices efficiently. But the actual application where it interfaces with the user is all edge, and we don't differentiate really too much from the sensor versus mobile device type of edge application.
Yes. Okay. And, okay, yes, Samuel, please.
Yeah, we also see the trend for the multi-layer AI combination for the whole system build up. So the first layer, the MCU, the tiny ML, the purpose is running in the always on in the very ultra low power condition. And when the event is detected, then we wake up the second stage edge processor and output the meaning for the metadata to the second stage and also to the third stage to the cloud. So we think in the future, we will see more and more the tiny ML combine the LLM application because LLM can run in the cloud, in the big edge, and the tiny ML running in the front end MCU device.
Yeah. Okay. One question to Professor Ye about education. Because I wonder, because students can access tiny ML EVB more easily, even they can access some cloud machine. But the question, they want to do some hands-on job. How do you suggest for the people? Because I believe some audience here are students. So do you have any suggestions for their career if they want to devote themselves in tiny ML? Okay. Not only writing papers, okay.
I think basically the tiny ML have the several unique challenges compared to the other, the AI models shown in the data centers. So basically we have the hardware. So the hardware, we have lots of the constraints. So for example, the microcontroller, we do not, the memory is constrained, the computer power is constrained. So how to design or create a very low power or energy efficient, this is a microprocessor. Okay, this is the one thing the students or the people who want to get into this tiny ML area should know. Okay, should know this. So the other one is applications. And if you want to know the associates or related, the tiny ML applications, basically, you can get the model from lots of these vendors. For example, the ARM has its own model rule, or the STM also has its own model rule, or even an NSP, or yeah.
Okay.
Yeah, so you can get these models from these vendors to understand what is the different model architectures compared to the one you see used in the cloud. Okay, so for example, the mobile nets or the squeeze nets, this model architecture is quite different from the ResNet or some of the Google Inception network. So you can learn the differences in these model architectures to more understand or to understand deeply about what is the unique or the challenges to use these AI models in the edge computing. Yeah. So in summary, you can understand from the hardware side, okay, to understand the limitation of the hardware. And the second one, you can understand from the software parts, even the model parts, to understand the limitations and how to apply these model architectures to the resource constraint devices. Okay, so you can then, or you can get into the tiny MLs from these two, directions.
Yeah, thanks. Okay, maybe any panelists have any answers want to echo to students here? Okay. Okay. Yeah.
So if I can add, I would like to emphasize one thing. Actually, I think in Taiwan, not only the hardware manufacture or design is very powerful. I think also the software development and also the academic research is also very powerful. So I think if we can combine these three together, maybe we can produce more sustainable, more powerful AI service or AI products to all the worlds. Yeah, and I think I would like to add one thing about the communities. Yeah,
Okay, yes.
and I think last year Odin has held a TinyML and Edge AI session in the largest open source conference in Taiwan. That's COSCUP. Yeah, I believe Jack also involved in this event. So I think if we can really, actually we have a lot of open source community in Taiwan formed by these software developers. So I believe if we can put these three things together, the industry, the community, and also the academic research, and also these three things together, maybe we can have more powerful AI products. So that's my 2 cents.
Okay, thanks, Ricky. Okay, then following will be the tough question from audience. Okay, anybody here want to raise any tough question to these tough guys? Anyone? Odin, you from ARM? Any questions? Because this morning the time is limited, right? So I'd like to reserve some space for the speaker here. If you like to answer some, give some question, okay, well, then we give answer here. Do you? Oh, yes. Thanks, Odin.
Hi, it's Odin. So actually, it's quite good. So I learned that. So I just want to thank everyone to, I think, the open-minded to use some of the technology from our company or take advantage of how to use some tool chain, about the technology to work together. So I think as we will try to create a platform that everyone can work together. So it doesn't matter you are the software engineer, you are the hardware engineer, you are the solution provider. So we want to try to do some of the organic ecosystem. So yeah, I just want to echo that a lot of panelists say that. So it's a lot of opportunity. So we can find some of the space for each of our business opportunity. That's just my thought. Thanks.
Okay, thanks, Odin. Okay. And Peter, do you like to ask some question about compiler or some benchmark? Okay, I'd like to introduce Peter from SkyMiser. He is also acting in ML Commons as MLPerf Tiny co-chair. So anybody want to do some benchmark research, you can come to SkyMiser and talk to Peter. And the question will be, Peter, do you have questions? Maybe you can raise one question to the panelists here.
Okay. Okay, thank you, Casey. And I'm as a volunteer in ML Commons Tiny Working Group as a co-chair, and I also joined the I think semi-monthly meeting in the Tiny ML Foundation. I know there's also another benchmark working group here in Tiny ML. Right now it's HAI Foundation. And I also, talking about benchmark, I wondering about, because we know some limitation right now in the MLPerf Tiny, there's only 2 image model, 2 audio model. If you have a chance to add a new model or suggest a new model, what kind of application you would like to the community to add on? That's my question.
Yeah, good questions. Okay. Yeah. Do you like to contribute some benchmarks?
I mean, we're definitely always interested in benchmarking because that creates that method of trying to compare performance and make sure that what we're building is is efficient, is able to meet our customers' needs. And sometimes, even as a vendor, when we're having conversations with our customers, the customers are not disclosing exactly what they're running. So the benchmarks, those like from MLPerf, become extremely critical for the end customer to understand the capability of the hardware without disclosing what they're doing to the hardware vendor or to any other service provider in between. So they act as a proxy. And I do agree right now that the MLPerf Tiny, or most of the MLPerf categories, the models being used are getting old. They get old very quickly. But you still need some level of commonality to be able to compare. I think we'd be very interested in seeing newer LSTM models, RNN type of models, to see how that has progressed and to showcase capability. I think on the vision side, There is a lot of content available that is maybe used to be big but can be run on smaller devices now. So making those part of the tiny category could cover the vision side, but I think outside of vision, there needs to be a few more models that are added there that can showcase sensor type of modalities or audio modalities better.
Yeah. Okay. Yeah. Okay. Okay.
Basically, we need to explore more tiny applications for by using these tiny metals. Okay, so in my mind is I would like to say if we can have more applications in the signal processing, or use the different kinds of the machine learning model. For example, the graph neural network. Okay, in the post automation, because this the model architecture of this graph. GNN, okay, graph neural network is quite different to the traditional convolution neural network. Okay, if we can cover or encompass this kind of the different kinds of the neural network architectures in our benchmarking, I would like to say it will be helpful for the advance of the tiny ML communities. Yes. So, in addition, I would like to say the tiny ML also have several this stream computing in the signal processing, or in this audio, audio applications. Okay, so if we can also take this the kind of the signal inputs data sets into account, I would say this also the one interesting part we can just try to consider and accommodate these kind of applications in the benchmark.
Okay.
Yes.
Yeah, thanks. Okay. Okay, Elda.
One thing about benchmarks itself, it's a bit challenging to have the same models running on all MCUs because many MCUs have very limited RAM and ROM. So if you start targeting larger models, it becomes challenging to target all MCUs fairly. But to extend the TinyML's benchmark right now, it covers, I think, one ResNet, one MobileNet, one autoencoder, and one DSCNN. It would make more sense to add maybe an object detection model, which currently there are a few that run on MCUs. Well, before they were like YOLO, which were pretty big, and now there are kind of nano YOLO that's run. It would make sense. And from a time series or real-time analytics perspective, it makes sense to add something in the realm of SVM. But SVMs are usually small, but it would also still be good for customers to see how they run. So extending it for different models and maybe stress testing the hardware for edge cases that were not explored before, such as different filter sizes for convolutions.
Yeah, thanks. Okay, so any question from audience? To you? Okay, so my last question is about robot, because the robot just like the elements everywhere. Human have the cerebrum, cerebrus. Okay, so I think for real time, for robot, the demand from the TinyML, maybe you have some opinion, right? Okay, what's the difference when we do things for robot based on the AI, the chips? What will you do? What is that? Okay, what can we do by existing AI vehicle, the tools or the chips? Because as I know, MCU originally it is for the consumer things, but next generation consumer will be robot to do something right. So I'd like to have your answers. The robot industry. Okay.
Just to understand better the question, sorry.
Okay.
I didn't get if you are asking about the roadmap or for robotic
Actually, my question is about, robot have so many sensors.
For robots, okay.
The sensors need to collaborate together, right?
Okay.
So the AI for that kind of will be another perspective, I believe so. So for the company like yours, a big company using MCU, maybe your next step for robot, what is the chip? What it looks like? Okay. Do you have any plan? Okay, because people hear always the MCU with the MPU. Okay. let's think about for robots specifically.
For robots specifically, okay.
Yeah.
Interesting question. So,
Yeah.
yeah, now there is also a little of hype on humanoid robots. A lot of companies, also Chinese companies, are releasing more and more humanoid robots. If you see now the basic architecture of a humanoid robot is basically you have just one centralized unit, okay, and you have a few sensors. You have much less sensors than what you would expect. Very few sensors in the humanoid robots, and basically you have a big Intel PC based or NVIDIA PC based GPU or in the humanoid robot, and basically is used for computer vision. So it's not so much a difference from let me say, a camera with a PC, okay? They give a little of the shape of the humanoid robots, but it's really a PC with a camera, as of today. In the future, what we see as a trend, and what we were discussing, is to have a decentralized architecture, where like a human, you may have a decentralized intelligence in a humanoid. So instead of having the hand that is just an actuator, you may have an intelligence there. So there are a lot of research at the university level about touching, okay, to get the sensation, okay. I was just reading an article this morning in the taxi. And basically, instead of transmitting all the raw data back to the centralized unit, you can have sensitive element in the fingers, and you can add an edge AI processor there, okay? So for that, do we need specialized hardware for humanoid robots? So far, I don't think so. We can use the devices that we are already using in consumer and in industrial, like microcontrollers and sensors with AI accelerated, also for humanoid, but they needed to change the architecture. They needed to change the architecture to a decentralized one. When you are starting to put the AI inside the sensor of the finger, inside the motor of the hand, inside the eye itself, where the camera, instead of sending the decentralized unit. This is where I can see, let me say, a possible evolution in humanoid robots.
Okay, thanks. So, Ali?
So from my perspective, it's also important to define there's the humanoid robots, there is robotics in terms of mobile robotics like AMRs, drones,
Okay,
etc.
different
So
robots, yes.
different types of robots, definitely. So in all of those, we're not defining the products or processors specifically because it's going into a robot. We do have devices that are where robotics is one of the business segments where they can be targeted. The AI piece fits into better sensing, better context awareness, so that can feed in through either vision or different types of sensor modalities and leverage AI to for the robot to understand where it is or what the situation is. And we're also seeing a lot of, and all of this requires more and more compute. So you're leveraging higher levels of compute-capable applications processors. You're adding more both CPU as well as NPU power performance to be able to handle not just the motion control or the trajectory planning, for example, if it's a mobile robot of sorts, but also the interaction as well. Interaction both in terms of within the space and with other users, but also voice, like leveraging LLMs into voice and conversational interaction. A lot of those add more and more compute needs to the overall, and the roadmap is built with that additional compute requirement in mind.
Yeah, so the sensor synchronization will be a multimodality use case, by different sensors together running. I just curious about, because big company, maybe you have sensor, you have MCU, and a lot of MCU come running together for multimodality models. Will be maybe next generation things, right? Okay.
Yeah, indeed, the multimodals is a very interesting topic. Obviously, the consideration I was giving for humanoid robots can be applied also to service robots. So this is also a market that we are serving, okay? Still, I see the same approach. In service robots, like the ones, if you go, I live in Hong Kong, there are a lot of service robots that are cleaning the floors in the, or bringing food to the hotel room, and they are going around. There are a lot of them. That kind of robots, they have much more sensors. They may have like 20 sensors, each of them, something like that. And in this moment, again, they are basically sending the data to a centralized unit where you are running, let me say, an algorithm. So two interesting points can be, first of all, a multimodal neural network architecture in the future. So you may get input from many different kind of sensors in order to get a better awareness of an environment. So you can add information from time of flight, audio, vision, and combine together in the same multimodal model. This kind of multimodal model can be, obviously, it can run on a centralized unit. At the same time, you can have, let me say, a mixed approach in which you are running a small model that is a local model, similar to the approach we were seeing this morning from the professor of the university. So you can have a small model that is already pre-processing the data, is sending the output, and eventually you can have a transformer based on an LLM that is just analyzing the output of the neural network model without the need to deal with the specific raw sensor, raw data of the sensors.
Yeah, thanks. Oh, Elder, okay.
So on the same topic, yes, I agree, like humanoids are not the only robotics that we have. There's robotics that's like a big area for us as well. But we target specifically in the MPU perspective for like, we have the RZV2H, which recently been released like a few months ago and has been quite successful for the robotics field itself. However, it is power hungry because it's an MPU, so you can add onto it. We have also something like a 16-bit microcontrollers, which is the RL78, and we also have low power 32-bit microcontrollers that you can add to this very big and MPU, and you can use it to manipulate and do inference of machine learning models. And then you can send that inference to the big MPU to do more advanced tasks to reduce the power consumption and to have faster response because an MPU still uses Linux. Okay. So you'll have like a big system working all together.
Yeah, thanks. Okay, Tyler's here today. Thank you very much.
Appreciate it. Thank you so much.
Okay.
This